Hi everyone. Let's talk about electric field. Electric field is defined as the electric force per unit test charge. So electric field E is F divided by Q, where Q is the test charge, right? So in order to find the electric field, then we have to know the electric force and then divide it by the test charge. So I have a particular scenario over here. Let's say that I have a charge plus Q located at the origin, right over here. This is my origin. And then I have a point P over here, which is at a radius vector r vector, and I would like to find the electric field at the point P. So what I do is I should put another point charge Q at the point P, and then use Coulomb's law to find the electric force first. So that would be K times Q, little q times capital Q divided by r squared, r hat. So that's the electric force. In order to find the electric field, then we just simply divide it by the test charge Q. So combining these two, we'll get the electric field due to a point charge little q at the origin is kq over r squared r hat, which is the same as kq over r cubed r vector. Okay, so that's the electric field due to a point positive charge. If, on the other hand, this charge was a negative charge, right? So if this charge was negative Q, then all I have to do is change the sign for Q, right? So this works for both positive and negative charges. Q plus means E along plus r hat or plus r vector, and Q minus means E will be along negative r vector. Okay, so if I wanted to now think about a positive point charge over here, think about what the electric field looks like around it, then the electric field at any point is just radially outward, right? Like we are seeing in this from this equation here, right? It just looks like if this charge at the center is a plus Q charge, the electric field is radially outward. And now if instead I had a negative Q charge, then the electric field is going to be radially inward. And that's what we are finding from what we just worked out. So we now have a combination of a plus Q and a minus Q charge oriented along the positive x-axis. Okay, so there's a plus Q charge over here somewhere on the x-axis and another negative Q charge somewhere on the x-axis. And we want to figure out what the electric field looks like all around it, right? So if I think about the electric field over here, let's just first talk about the directions. So the direction of the electric field due to the plus Q charge is going to be in that direction. And the one due to the negative Q charge will also be in that direction. And so these two electric fields will add up to give us a large electric field in the middle. On the other hand, if I think about the electric field at this point, the plus Q charge is going to create an electric field pushing the unit positive charge away, but the minus Q charge is going to attract it. And the minus Q charge, because it's probably closer to this point and the charges are equal, plus Q and minus Q, the minus Q charge will have a larger effect than the plus Q charge, which is further away. And so we can think of the effective electric field be in that direction. Okay, and now if you go to a point over here, then the plus Q charge is repelling very strongly and the minus Q charge is attracting not as strongly. So the electric field is probably going to point in that direction. Okay, so now we see a way to figure out the electric fields along the x-axis. In order to figure out the actual magnitudes of the electric field, you'll have to know these distances. For instance, for this point over here, you'd have to know this distance x, and you have to know that distance L. And if I know those two distances, then I could work out the electric field. For instance, in this particular case, if I call this point P and I want to figure out the electric field at the point P, then first I have to check the quantity of electric field due to the plus Q charge, and that's going to be equal to KQ over x squared. And this is along the negative x hat direction. And for the negative Q charge, then we'll have plus K times negative Q over, and this distance from point P to the negative charge is x plus L, right? So x plus L whole squared, x plus L the quantity squared, and then this one is due in the x hat direction. Okay, so now if we put these two together, then we get negative kq x hat in the numerator divided by x squared times x plus L squared, and then we will also multiply by x plus L squared plus x squared. Okay, so that's our electric field at the point P. Depending on what L is, we will find result for it. But generally, if the two charges are exactly the same, then this number you can see is going to be a negative number times x hat. And that shows you that this electric field is going to be in the negative direction. Okay, we can do the exact same thing for other points. All right, so now let's take a look at what happens if I have two positive charges also along the x-axis, and I would like to figure out the electric field again at multiple points. So if I have a point P over here and I want to find the electric field, these charges are both positive charges. So this point is being repelled in both directions by both the positive charges. So you can think of a point in between where the electric field is actually zero because of cancellation. Similarly, at this point, there is an electric, both plus Q charges are pushing the unit positive charge. So the electric field is outward. And similarly, if you go here, the electric field is also outward because both positive charges are on the same side, so though they are both repelling. Okay, we should probably also consider a generic set of other points not along the axis. So for instance, in this previous problem here, if you go to a point like this and want to find the electric field, you can think of the electric field being in a skewed direction because due to the negative Q charge, this point is being attracted, but the plus Q charge is repelling like that. And so depending on where the point, this point P is located, you'll then have to do a addition of vectors, right? So vector addition will then tell you the direction of the electric field. But generally, because at a skewed point not along the axis, the point P will have different pointing arrows as the electric field or electric force due to the two positive or any combination of positive and negative charges. So you can tell that the sum total of this will never be zero. So the electric field cannot be zero anywhere outside of the line that is joining the two point charges. So that's a key idea. E equals zero, not possible, right? It's not possible outside of line joining two charges. And this is true only for a configuration of two charges. Of course, if you have more than two charges, then this will not hold any longer. Let's work on a problem to illustrate this idea of electric fields and electric forces. So this particular problem says that two charges Q1 and Q2 are placed at x1 and x2 along the x-axis. Find a spot where a charge Q can be placed so that it does not feel any force. So I want to place a charge Q at this arbitrary location along the x-axis, so I've called it to be at a distance x from the origin. And then I have placed the two charges Q1 and Q2 at x1 and x2. So this one is Q1, this one is Q2, and they're at x1 and x2 respectively. Okay, so now we want to figure out what is the electric force on Q. And we have been told that we have to place Q such that it does not feel any force. So if it does not feel any force, that means F equals 0. If F is equal to 0, F is nothing but Q times E. And we know that Q is not equal to 0. So as long as electric field E at that point is 0, we are good to go. So see that in this particular problem, the charge Q is not even needed, right? I do not need to know that there is a charge Q. All I could do is I could figure out the electric field at this point P. Let's call this point P. And once I've done that and I've set it equal to 0, I'm good to go. So that's exactly what we're going to do. So the electric field at E due to the charge Q1 would look like KQ1 divided by the distance from Q1 to the point P. So that's going to be x minus x1. So x minus x1 squared. And then this is going to be, because we don't know what Q1 is, we're going to assume that Q1 is positive. So this is going to be along the x-hat direction. Okay, let's do the same thing for Q2. So, and then add these two together, or let's talk about the electric field separately. So E2 is due to Q2, so that's K times Q2 divided by x minus x2 squared x hat. And so these are the two electric fields due to the 2-point charges at P. And then to find the net electric field as before, we will say E equals E1 vector plus E2 vector, right? So this will bring us to KQ1 over x minus x1 squared plus KQ2 over x minus x2 squared x hat. Okay, so now if this electric field has to be 0 vector, x hat is not 0, and k is also not 0. So we get an expression that looks like q1 over x minus x1 squared is equal to negative q2 over x minus x2 squared. Okay, and this is a quadratic equation that we can now solve. Okay, quadratic solve to figure out the value of x. Note that I have purposefully talked about Q1 and Q2 without any signs, right? So if Q2, for instance, was negative, you'd have to put in a negative value over here. So that would make it make both sides of the equations automatically positive. But generically, you don't have to plug in the values of Q1 and Q2 before you have actually solved the problem. So let's try to attempt to do that. So from here, if we invert this relationship, what it is going to look like is x minus x1 squared times Q2 plus x minus x2 squared times Q1 is equal to 0. And now we can sort of break these parentheses, and we will have x squared minus 2x x1 plus x1 squared times q2 plus x squared minus 2x x2 plus x2 squared q1 is equal to 0. Okay, we can go further and we can write q1 plus q2 times x squared, okay, minus 2 times q1 or x1 q2 plus x2 q1 times x plus finally we have x1 squared q2 plus x2 squared q1 equals 0. And as you can see, this is a quadratic equation, and the solution to this quadratic equation is not very difficult. We know that the solution to quadratic equations of the form, just to remind you, ax squared plus bx plus c equals 0 looks like x equals minus b over 2a plus or minus square root b squared minus 4ac over within the, if we put the 2a inside the square root, we get 4a squared. Okay, so using that idea, we can just write that this x is equal to negative 2 times x1 q2 plus x2 q1 divided by 2 times q1 plus q2. Great. And then we have plus or minus square root of b squared, so that's 4 times x1 q2 plus x2 q1 squared minus 4a times c, so that is 4 times q1 plus q2 times x1 squared q2 plus x2 squared q1 divided by 4 times q1 plus q2 squared. Okay, so here we can actually simplify this problem, this answer a little bit, and write x equals, the 2's will cancel, the negative signs will cancel. So we get x1 q2 plus x2 q1. That's the first part, plus or minus square root of, here again you see that the 4's all cancel. So this is a square root of the stuff that is appearing over here, which is x1 q2 plus x2 q1 squared minus q1 plus q2 times x1 squared q2 plus x2 squared q1 divided by q1 plus q2. And that's our result. Okay, so this is a problem with the orientation along the x-axis, right? But what if my orientation was not along the x-axis? So what if I have 2 points, 2-point charges q1 and q2 that are oriented like this? So let's say that we will put the q1 at point 0, 0 and the q2 at some point x, y. In that case, you can tell that, again, if I were to find a spot to put another charge where the electric force has to vanish, I still have to figure out what is the electric field around the combination of these two charges, and specifically where does the electric field vanish. And this would again only happen along this line. Okay, so one way of treating this problem is if you rotate everything to make it be along the x-axis. Okay, and then this maps to the previous problem, and you can just figure out what is the distance of the point. So let's say that this one is the origin, and the second point is at some value x1, and then what is the point x where the electric field is 0, right? So what is the point x for E equals 0? And this should be exactly the way we worked out the previous problem. Now, once we have that answer, we know then that this distance over here is square root of x squared plus y squared. And we also know the angle between this line and the x-axis, and that's just equal to tangent inverse of that, theta is equal to tangent inverse of y over x. So all we have to do is find a point along this line somewhere over here which has the same exact distance as the solution to this part of the problem, right? But is at an angle theta equals tangent inverse y over x. And that's essentially the method that you can use to solve a problem of this type. We're not going to explicitly solve this problem, but if you have questions, please feel free to email me at bbhattach@ltu.edu. Thanks a lot for watching.